what a set is we will not define, what membership is we will not define. But then it is difficult if you do not define anything and you are using a technical term, are you confident that you are using it correctly? That brings up always this question, right. In fact, it becomes correct because the properties what it obeys, that is enough for us. Anything else if you say it instead of set or membership, but it has those properties, it is enough. That is how we will be proceeding. So, you become slightly matured in using the language. You do not know exactly what it means, but if it means something around this, it is enough. That is the idea, right. So, that happens in mathematics also. Set is what membership is, we go for their operations on the set, say union, intersection, remember those things, yes. So, we will not define them, I am just brushing it up. Now, then you have different subsets, okay. Then power set, okay. Then their properties of these operations. So, power set always has more elements than the set itself. You can prove it, can you? Yeah, but it needs to define what is the number of means, fine. For example, take the set of all natural numbers, okay. How many elements it has? Infinite elements. So, take its power set, how many elements it has? So, how do you say it has more elements than that? It is infinite. Raise your hand.
Elements from each member of the set A, all of them are present in the power set,
Right.
as separate. So, power set at least has the same cardinality as the
Important, cardinality. Please continue.
So, yeah, so the power set at least has the same number of elements or cardinality as the set A, which you are looking at. Plus, you can always consider one more element at least. Say it's a combination of just 1, 2 for a set of natural numbers. So, it has at least one more than the number of elements in the set A. So, you can say it has more elements.
Okay. That makes sense, but not exactly. Let us try to make it exact. Okay. So, first thing is cardinality you have used, which you do not know. We know, of course, we have not brushed up till now. Okay. So, we have this number of cardinality, these are used synonymously. Okay. So, the problem is what is number of, we can define in finite sets easily perhaps, in infinite sets it can become difficult to define. So, what we can do is we can compare sets for their number of, for their cardinality. Okay. So, how to compare? It reminds a story. See, there was one person who was in Africa on a safari. So, he found one tribal people. So, the tribal people had only 3 types of numbers. It was strange for him to accept in the beginning. He found they have 1, they have 2, then they have many. If you ask somebody how many sheep he is having, he will say many. It does not have a number, how many, it is not 100, it is not 105 and so on, it has only many. The thing is, he is not missing one of his sheep, how? So, it is comparison, he does not have a name for that number, but he knows how many. See, in a bag he just keeps a people for each sheep. So, when in the evening they come, they allow one sheep and then put out one from his bag and it continues, right. So, it is possible by comparison even if you do not know the name of the number, right. So, that is more basic, we will use that. So, one sheep, one pebble, it defines a function, a 1-1 function. If it is over, then it is onto function. Okay. So, that means we say that if a set C is there, if a set D is there, I have a function f from C to D which is 1 to 1 and also onto, we will say that C has the same number of elements as D. Is that okay? fine, agreed. Now you can think so many other things from this. If there is a one function g from C to D which is 1 to 1, I do not have any information on its ontoness, then what do I say? C has at least that many elements as D, is that right? If it is onto, then if there is a function h from C to D which is onto, then yes, C has no more elements than D has, is that okay? Fine. So you can have some bifurcations there, but this is the standard way of comparing them, anyway by 1 1 onto functions, fine. So now when you say a set cannot have more elements than its power set, what do you need to show? We show that
If it is 1 to 1, then we can say that it has more elements than.
It's 1 1.
well that is easy to show that there is a 1 to 1 function, because you have already done it by taking the singleton sets. You have a set x and you take its power set, you will write 2 to the power x symbol, and you can always define a function f from x to 2 to the power x by what? X in capital X goes to the singleton x. Okay, we can always define like this. Is it 1 to 1? Yes, it is 1 to 1, because you can't find two elements whose image, that singleton, will be the same, right? Is that okay? So it is 1 to 1, therefore always x will have at least it is not at least as many elements as, you can't say as many elements, right? At most that many elements as in its power set. Okay. So let us forget this at least, at most, if it is confusing. We will say cardinality of x is less than or equal to cardinality of its power set. Okay. So because of this 1 to 1ness, so we say cardinality of x is less than or equal to cardinality of its power set. Clear? Now the question is the other one. That is why I said it is easy to prove what you told, but it does not prove what you wanted to prove. You want to show that x does not have that many elements as in the power set. Okay? Is that right? It does not show that. It still has a possibility that there is one x whose number of elements is equal to the number of elements in its power set. Is that okay? You have less than or equal to. So what is required to be proved? Yeah.
Show that 2 bar x has an null set which is not where it always 2 bar x will always have a null set. Power set of x will always contain null set as a member of 2 bar x. So you can show that it will always be greater than.
Well, you want to say that this function, what we have defined, is not an onto function. Right? Agreed? This is not an onto function, it is clear. Either you take the empty set in this place, okay, or you take a set having 2 elements, it is not an image of any element, right? Is that okay? Provided there are at least 2 elements in X. If there are not, then you cannot do that, but that argument is fine. Empty set is there, which is never is an image, but this does not prove that for any x x will have less elements than its power set. It only proves this function which is 1 to 1 is not onto. There can be another function which is 1 to 1 and onto. Okay. Is the issue clear? First you must understand the issue, then try for the solution. Is the issue clear? We have tried to construct a function which is 1 to 1, we find that it is not onto. So, it might be giving us some push for our belief, yes perhaps we are correct, but not yet. You can try some other 1 to 1 functions, constructing them, see whether they are onto or not. That is your experimental stage, which mathematicians never reveal. Any 1 to 1 function there, you will see that it is never onto, right. Will that prove? Will that prove? Yeah. Even you say there is no function which is onto, will that prove? Yeah, proofs. So, let us try one of these, whichever way it goes. We will have to try to discover the proof now, right. So, we have two options open here. You can take any 1 to 1 function and prove that it can never be onto, or in general you take any function so that it can never be onto, right. It is easy to construct one function which is not onto, but we are not interested in that. We are interested in the other question. You give me any function, I will show that it is not onto. This is the contention. Is it clear? Okay. Now, how to proceed? That is the problem. Let us take a function g from x to 2 to the power x. We want to show that it is not onto. Okay. So, that means there are some elements in the power set which are not images of any elements in x. Whatever way this g goes, it does not matter. G sends elements to of x to elements of the power set which are subsets of x, right. Is that clear? G sends elements of x to subsets of x which are in the power set. Now, we have to see that there is one element here which is not an image of any of these elements in x. Clear? This is what our aim is. Fine. Okay, that is easy to get if you have some exercise before it, but I will give you one other way of looking at it. There is a temple in South India where you go and throw a coin to reach the top of the temple. If you see that it never comes back, your wish is fulfilled, right. God has accepted it. If it comes back, your wish is not fulfilled. That is the way people believe there. Now, as a student of IIT, you want to disprove it. You want to show that it is not correct. So, what wish you should have while throwing the coin? Yeah. Now, prove it. Your wish works. Yeah, continue. Continue.
Okay.
You can do it. Now, anybody else?
Yeah.
Just try to think a bit. You don't have to produce immediately. He says, what's your name? Sekhar. Sekhar says that you wish the coin should come back, right, and then throw the coin. Now, what will happen? Wish is fulfilled, but the people believe that if it comes back, your wish is not fulfilled. So, that part is wrong. In the other case,
if it stays, then your wish is not fulfilled.
Not fulfilled, but people say that. So, anyway, you have proved. It has something to do with this proof. That is why I told. So, look at the elements in x and look at its images, right. Here we have one function f which is taking x to singleton x. This x is a member of its image. Will it always happen? For any function you take, will it happen that the element on the left side, right, and its image on the right side will have this relation, x belongs to that image? Maybe, may not be, right, because any arbitrary function we are taking. Okay. So, it is meaningful to ask this question whether x belongs to g of x. Is that right? See, g of x can be empty set also, in that case it does not belong, but other cases we can say we need to know what this g is, fine, we do not have any information, but we will use it somehow, this question. So, the question now is coming whether x belongs to g of x. Answer can be anything, x may belong to, x may not belong to, it depends on g, it depends on this particular x. Okay. Now, let us look at one set, let us say y, which is equal to the set of all elements of x which satisfies some property. Okay. The property is that x does not belong to g of x. It takes some time to understand, because we are not giving any construction, thinking that you are matured enough. Okay, let us look at it. It has relation to that story. We are picking up all the elements which contradict that. Your law, some law, one of the laws we have picked up, find out all the collection of those elements. Now, we are going to prove that it is not possible that the belief is tenable. Right. So, here our procedure is to show that this y is never an image of any element in x, right. If it is, then there is some problem. Okay. Is it clear? So, now suppose on the contrary, suppose I have an element y which is in x such that g of y is equal to this set capital Y. Okay. So, notice that I am not writing everything, there exists one y in x, in fact there exists some element whose name I am writing as y. Okay. If you write there exists y, that y you cannot use, it can be something, some other name also, alpha, beta. So, in that sense we are not writing every detail here, we are telling there exists one element, call it y, which has this property, g of small y is this set. Okay. Because we want to show that it is not possible to have any y of which this one is the image, right. So, on the contrary, this will be assumption. Now, you have to see some contradiction is happening, it is not correct to assume like this, right. So, this is a proof by contradiction. Well, so once this y exists which is in x such that g of y equal to capital Y, we ask the same question now, what happens to this y and that g of y, right. So, our question is it that okay. Have you gone on scout sometime? You would have formed knots and then how to unthread the knots and so on. So, it is a nutty affair now. We are proceeding slowly, but there are only 2 knots, not many. Okay. So, first what we have done, we have asked a question which looked meaningful, From there we constructed a set, take all those which are not in their images, then we formed a set. Okay. There is a set anyway, it is a subset of X, it can be empty, we do not know, but it does not matter, whatever it is a subset of X. Then we are telling, suppose there is one element whose image is this set, then that element is a member of this set or it is not. We are too curious. Well, let us find out what happens. Again, suppose y belongs to y, then what happens? What happens? Small y should satisfy its property, right, because that is the definition of y. So, that means small y does not belong to g of y, is that right? Okay. But g of y is what? Y. Therefore, what happens? Y does not belong to y. Do you get a contradiction here? Contradiction to what? Which assumption gave the contradiction?
Suppose y belongs to y.
Suppose y belongs to y. Then you get y does not belong to y. It is not that this has been contradicted yet, right, because there is the other case, y may not belong to y. So, in fact, this proves that y does not belong to y. Do you see the proof? But anyway, we are not worried about that. What it says that probably y does not belong to y, there is another case, let us take it up. So, now suppose y does not belong to y, and what is y? Capital Y, g of small y. So, this says y does not belong to g of small y. Right. Capital Y is equal to g of small y. So, I have just replaced that. Fine. Here y does not belong to capital Y. Now, this capital Y is equal to g of small y. So, by replacing that I just get small y does not belong to g of y. But now, small y does not belong to g of y is the defining property of capital Y. Therefore, small y belongs to y. Now, we have a contradiction. Look at it, we have a contradiction now. It says if I assume y belongs to capital Y, then small y does not belong to capital Y. If I assume small y does not belong to capital Y, then small y belongs to capital Y. So, both of them gives the contradiction that y belongs to y if and only if y does not belong to y, that is a contradiction, right. And for that contradiction responsibility goes here, fine. Therefore, G is not onto. Okay. So, any function you define from x to its power set, it will never be onto. Is that okay? This is your famous Cantor's theorem, which says that cardinality of any set is always less than the cardinality of its power set. It can never be equal to it, right. This does not prove that, this along with such an f proves it, right. Any function which is not onto, okay, might tell you that there is a possibility that the other set which is the codomain may have more elements, but it does not prove it. The proof comes from this one, any function you take, that is never on 2. Therefore, X always has less than or equal to elements in power set of X, but it has less than or equal to is proved by demonstration of an on-one function, not by this. Is that clear? Okay. So, this will be helpful later when we come to comparing cardinalities. Now, because natural number is countable, so 2 to the power set of natural numbers is having more elements than the natural numbers, you have to give a name for it. So, you say it is uncountable, right. When you count because of natural numbers, even if it is infinite, we say it is still countable, right. So, countable is not a name for having finite things, it is finite. Countable can have finiteness or it can be infinite, but like natural numbers. Okay. So, which is in one-to-one correspondence with natural numbers, okay, or it is in one-one correspondence with an initial fragment of natural numbers, which is finiteness. Is that clear? And every other set is called uncountable. Okay. We are not going again to the details of that countability uncountability theory. In uncountability itself, there can be many types of uncountability, right, like power set of natural numbers, it will have more elements than the power set of natural numbers, but all of them are termed as uncountable. It is too big for us to handle now. Okay. If we need, then we can give them some names, there are names for that. Okay. So, this is about something we need about the countability and uncountability, fine. You will need something about formal languages, they are again a countable set. You might have already some exposure to it, but we will just again brush off. Okay. So, suppose I take one set having some symbols in it and so on. So, x1, x2 and so on, they are symbols, right. So, they are just elements, we are calling them symbols in this context, that is all. But when you say symbols, there is another connotation to it, that no symbol is a part of another symbol. This is funny, in some Tamil characters you might find a symbol is a part of the other symbol, right. For example, straight line, something like this, that might be a part, it can be a symbol, it can be again part of another symbol, that is possible. We are not assuming such things here, we are taking them away, we are telling that our symbols will have such characteristics, none is a part of another symbol, right. For example, you cannot get this and this as two different symbols, right. We will not call this a symbol and again this also another symbol, it can be concatenation of two symbols, one is this one, the other is this, right, but it is not independently as a symbol. That is our understanding, we are not formally defining what a symbol is anywhere. Okay. Now, let us take this alphabet of some symbols, this is called an alphabet, just like our usual languages, fine. Then you define a string over this alphabet sigma, a string over sigma, it is just a finite sequence of symbols from sigma, right. So, we will be writing it as something like S equal to xi1, xi2, xi3, xim. So, there are m symbols here, which symbols are not fixed, not x1, x2, xm, right, any symbol they can be. This xij's can be from anywhere in sigma, but it looks like this, any string from sigma will look like this, any symbol from sigma is each one of them. Is that okay? So, it is a finite sequence of symbols. Then by sigma star we will write as the set of all strings over sigma. and then when you say language over sigma, it is just a subset of any this sigma star. So, you say a language over sigma is any subset of sigma star. So, which means a language over sigma is some set of strings over sigma. Okay? They are finite strings, not infinite strings. We are not using string in that sense. Always we are keeping us to finite sequence of symbols for strings, right. So, these are the basic things of formal languages. You want to describe a formal language, start with some number of symbols, then define some strings. Take a set of strings, this defines a language over that set of symbols. That set of symbols is called an alphabet. Okay? So, it is wrong to tell A is an alphabet, B is an alphabet, C is an alphabet, or in the Roman alphabet A, B, C are alphabets. It is wrong to tell like that. The alphabet is the Roman alphabet, which is the set containing A to Z, small a to Z, 0 to 9, comma, semicolon, all those things, details, right. So, that is the way it is being used here. Sigma is called an alphabet, all others are symbols from the alphabet or alphabet letters. Then you take the strings, take a subset of strings, that is a language over sigma. Fine. We may have to use this language over some defined symbols, take some symbols, define a language, then give some connection over that language. This is what we will be doing later. For that we may need one or two more concepts, like the concept of a prefix. Okay. See, these are just some technical words which we will be using later. That is what we are explaining. For example, take the word prefix. So, here pre is a prefix of prefix, right. P is a prefix of prefix. Okay. RE is not a prefix of prefix. Fine. Prefix is a prefix of prefix. Okay. If there is nothing I write here, that is also a prefix of prefix. But it is difficult to leave it like that, is it not? If I write nothing and say that that is a prefix of prefix, it will not make sense. We will not be able to talk about it. That is the problem. Probably it makes sense, we will not be able to talk about it. So, let us give a name to it. We will say that as the empty string. Which will write as epsilon. So, there are no symbols in it, right. So, the empty string is also a prefix of any string. Okay. Now, what is a prefix? Yes, can someone define?
A consecutive set of symbols from the beginning of a string is a prefix, starting from the beginning of the string.
You need beginning, you need consecutive to define it. Well, we will define it in a better way. We will define only one idea, which is called concatenation of strings, right. So, prefix is a concatenation of two strings, pre and fix. So, this is or the concatenation of strings pre and fix. Okay. We are using the word concatenation here, which we seem to know. right. So, it means if u is a string of symbols say x1, x2, x3, xm, and then v is a string symbols y1, y2, y3, yn, then u concatenated with v gives a string which looks like x1, x2, xm, then y1 up to yn. Is that clear? That is the idea of concatenation. Fine. Now, using the word concatenation, can you define prefix?
The first string in
If it is possible, A is a prefix of B. If it is possible to get B by concatenating some string to A.
Some string to it. Is it clear? U is a prefix of v, if and only if there exists a string w such that u w equal to v. So, by saying u w means concatenation of u and w. Is that okay? So, just following this we will write concatenation without putting any symbol in between the strings. Fine. So, that means we will write concatenation of u v is u v. We will write like this. Then what we say is u is a prefix of v if and only if there exists a string w such that u w equal to v. Okay. So, prefix is defined now. Then let us take two strings. We do not know whether one is a prefix of the other or not. Let us think of two strings arbitrarily. Take a prefix of first one, prefix of a second one. What connection they may have? Not necessary, nothing can be there. One is epsilon, another is u, then there is something. But if I take x1, x2, another is y1, y2, no connection, right. But if I take a same string and two prefixes of it, then yes, you are correct. Is it clear what I am telling? Right. Take prefixes u and v of the same string w. Now, you may say there is a connection between u and v, right. What connection it is? Either u is a prefix of v or v is a prefix of u or u equal to v, right. So, one is a prefix of the other. Let us write it first. Okay. So, we are implicitly using our alphabet, the alphabet is sigma. Let us write it now explicitly. Well, you know the result. Okay. You want to show the result. Can you suggest which proof method really does that? In mathematics, there are so many ways of proving. One method uses always the known result. If you know the result, then you can use that proof method. If you do not know it, you cannot proceed from the beginning. Induction, mathematical induction, right. Once you know what is to be there to be proved, you can prove. Before that, never, nothing can be done. You can't use anything, right. So, now suppose you use induction, what will happen? Induction on what? that is the first question, right. Induction on what? Let us have induction on W, right, but W is not a number. How do you have induction on it? How big is it? So, induction on that is called the length of a string, right. So, what is the length now? Length of a W is what? Number of important. So, number of occurrences of symbols, right, that is important, very important there, because your alphabet can have only one symbol 0, still you can have a length of string 10, all of them are zeros, right. So, it is the number of occurrences of symbols in W, but again we have to define these occurrences, repetitions. We are too misers. So, what we do? We will use concatenation. Since we know what concatenation is, we will use that. How do you use it? Again, you define it by induction, right, because concatenation slowly increases the length of the strings. You can visualize that way. So, you can use it to define what is the length of a string, fine. So, length of the empty string is 0, length of any symbol is 1, then go to the next stage, find out one symbol either as a prefix or as a suffix and then define the length. Is it clear what we are doing? So, we will say length of the empty string is 0, fine. Length of a symbol is 1, fine. Now, if length of U equal to m and take a symbol from sigma, okay, then length of sigma u, or you could have written u sigma, either way you define it, is equal to m plus 1. Is it okay? So, this is a definition by induction. You can use induction as a proof method or as a definition method also, fine. So, this implicitly defines length has to be a natural number. Now onwards our natural number will include 0, otherwise you will always have to say non-negative integers, that is very awkward to speak always. We are natural people, we will take 0 as a natural number, fine, agreed. So, length is a function from the set sigma star to natural numbers, which is defined this way now. Is it clear? Now, then you can use length to prove the prefix lemma, length of W.